Hello everyone. I wanted to talk about niobium. It's element 41 on the periodic table. And it is right here. And when I first heard about niobium, I'm like, what the heck's that? I've never heard of it. But it also goes by Columbium, and I have heard of that one. And so that's what I'm more familiar with. Okay, so it's going to be pretty important. Because you're going to see how many things it's used in. Alright, it's a relative in tantalum, and actually they named niobium after Niobe, which was the daughter of Tantalus. Okay, they're always naming the Greek gods. Alright, I'm not going to go into all that's in here, the history of it or anything like that. It's just a lustrous gray ductile metal. Okay, and if you want to read more about all the stuff about it, you can. What I want to get into are the production of it and its uses. Okay, first of all, it's really only found in two primary, well, really only one, but there's another one too. Brazil and Canada are really the only ones that, at least what the USGS estimates, are making it. And in Brazil, they're estimating about 58,000 tons a year, and Canada 4,400 tons a year are coming out of their mines or resources wherever they're finding it. And I'm going to get into all that. Okay, so what some of the applications for it are for steel production, superalloys, that would include jet engines, gas turbines. It was used in the nozzle of or an alloy of it was used in the nozzle of the Apollo service module. I find it interesting that clear back in the 60s they did an alloy called C103. That's probably, the C is probably for Columbium, but made for liquid rocket thruster nozzles. Okay, so that was that Apollo lunar module and some other stuff. I'm sure they were making it for that. Okay, interesting. The nozzle of the Merlin vacuum series of engines developed by SPACEX for Falcon 9 is also made from a niobium alloy. Okay. Let's see. Superconducting magnets. Now, this is a very important part, I think, for niobium. It's used in MRIs and other nuclear magnetic resonance instruments. And it also says as well as particle accelerators. Okay, so the LHC is using 600 tons, while the International Thermonuclear Experimental Reactor is using 600 metric tons of niobium tin strands and 250 tons of niobium titanium strands. And this is going to be really big business because, I mean, this is even an old statistic. Oh my goodness. 92, 1 billion worth of MRIs were constructed with niobium titanium wire. Okay, so it's used in some pretty important stuff. Okay, it's also used for superconducting radio frequency cavities, and that is used in a couple different things. The XFEL, which that just started 4 months ago, and just go back here a minute. I already showed you that. This is what the SPACEX nozzle looks like. Well, actually, I think it's the whole engine, but so the nozzle for that is niobium alloy. Okay, this is the XFEL, and it is European X-ray free electron laser, but it's actually, the location is in, or it's housing the superconducting linear accelerator at the DESI Research Center in Hamburg. Okay, so it's another linear accelerator use there. Okay, Fermilab uses it. Okay, these are what the cavities look like. And that's pure niobium right there. Okay, also it will be used at the LCLS2 at the Stanford National Accelerator Laboratory and the PIP2 at Fermilab. Okay, so going to, I think I skipped that, but we'll go back to it. So there's the research facility there, and what it does is it centers its research on atomic and solid state physics and chemistry, mostly seems like regular commercial applications. Let's see. It says advancement from the LCLS2 will be from the discoveries using this new capabilities, may include new drugs, next generation computers, and new materials. Of course, the new materials, you never know what they're going to be talking about there. Okay, and then Fermilab, there's the cavities, pure metal there. Okay, and the PIP2 has to do with the deep underground neutrino experiment. Okay, where part of it is at Fermilab, the near one, and then the far one is in the Stanford lab in South Dakota. And what they're going to be trying to test, it says the primary science objectives of DUNE are to investigate neutrino oscillations, determine the ordering of the neutrino masses, and search for neutrinos beyond the currently known 3. And one of the ones they're searching for is the sterile neutrino. Okay, and what that's going to be looking for is, let's see here, oh, it's up here, trying to find dark matter, dark radiation, things of that nature. Okay, have I gotten to, okay, that's just the place in South Dakota, and that was part of DUNE, and it says that it's going to look at neutrino scattering, dark matter interactions, a lot of dark matter stuff. What's that? Okay, let's see. I skipped one. Okay, the International Linear Collider is something new that they're working on, and it's going to be in Japan, and it's going to use quite a bit of it. Niobium. One thing I learned about this that I didn't know that I thought was interesting is that Linux or linear accelerators are a little bit different than the synchrotrons, which are the circular ones like the ones at the LHC, in that in the Linux ones, they when the particles collide, they disappear, whereas the synchrotrons are available for future collisions. And I didn't know that, but one of the dangers of it is that it can lead to synchrotron radiation. But I didn't know that the ones, like for instance at the LHC or other circulating colliders, I didn't know that um, they were still available there. Okay, now one of the things at the ILC that they're going to be looking for are they hope to be able to measure the mass, spin, and interaction strengths of the Higgs boson, and if existing, measure the number, size, and shape of any TeV scale extra dimensions. Investigate the lightest supersymmetric particles, possible candidates for dark matter. And so it's not built yet, but most likely it's going to be in Japan. Okay, another use for this element is D-wave. Okay, now, okay, let me go to this first. No, that's not what I wanted to do. Well, first, I should have had the other one up first, but I'll just tell you that before I get to where it says it's going to be used and how it's going to be used in D-wave, I just wanted to point out that, and this is kind of a neat, they have a couple tutorials that are kind of neat, but one of the things that it says at the end is that these quantum computers can learn, which, you know, if you've watched the TED Talks that Jordy Rose gives or other lectures, you've known that, but I think that's important, that they're actually learning and programming itself. And so I think that's important to know, and also that uncertainty is a feature in the thing. Uncertainty is a feature in the answers that D-Wave gives out as well. Okay, so you know they might give an answer that you're not expecting, and then who knows what you're gonna get. I mean, it takes some discernment. Okay, so the other tutorial. So this is a nice tutorial as well. The quantum hardware. There's a lot of stuff in here. Okay, this is what I wanted to get to. The SQUID is a quantum transistor. SQUID stands for superconducting quantum interface device. Okay, and the niobium is this ring right here, is what he said. Okay. All right, and that is what an 8-qubit looks like. 4 there and 4 the other way. All this stuff's really neat. Sometimes I like looking at all this stuff. Okay, that's the 128 qubit quantum processing unit that was used in D-Wave 1. And you guys probably already know, but this thing is kept so cold, basically absolute zero. I think they said 0.015 above 0, absolute 0 Kelvin. Okay, now I found this history of the D-Wave interesting because I didn't know that. You know, in about 2007, they only were using 4-qubit, 16, 28, 128 in 2012, 512, then went to 1000, and then that's what they're selling now, and then soon it'll be 2000. Okay, and that's what it looks like. It's approximately 10 by 10 by 10 feet. Okay, there's where it talks about, yep, 0.015 Kelvin. Right, I like looking at this stuff, but I'm not going to go into all of it, but I just wanted to kind of show you what's there. Okay, now what they're doing when they're calculating all this, and like, 2,000 qubits, oh my goodness, what it's doing is it's modeling a problem into a search for the lowest energy point in a vast landscape. I would say so. The processor considers all possibilities simultaneously to determine the lowest energy and the values that produce it. Multiple solutions are returned to the user, scaled to show optimal answers. Okay, so they're looking for, oops, those low points. Okay. All right, now, how many possible answers are there? Well, if there's 2,000 qubits, the possible answers are 2 to the 2,000. And that number, I can't even, I mean, who the heck knows what it is? 1.15 times 10 to the 602. So, kind of crazy. All right, and then I forgot about a couple other uses of the niobium that I wanted to get into. Other uses of it are electroceramics, optical modulators. Oh, it's hypoallergenic, so, jewelry applications and prosthetic implant devices, coins, the commemoratives. Sodium vapor lamps, arc welding rods for stainless steel, and it's a catalyst for the oxidation of propane. So lots of uses. Now I do want to go back here and say that it did say that 90% of it was for steel production. So, but still, that this other stuff is going to increase. That it will. And the pure niobium, this is a video saying that, they realized that they couldn't get it anywhere, so they built a foundry for it in Silicon Valley. Now, I don't know if they commissioned it or if they own it or what, but it is owned all in one place for pure niobium, so that's kind of odd that it's all being used for all this quantum stuff and there's only one foundry for pure niobium in the world. I found that odd. But let me know what you think in the comments, and I hope you have a great day. Talk to you soon.